So in this video for this week, we're not really doing anything new calculation-wise. We're just extending our calculations to a little bit more complicated problems. And so we're going to do some together in this video, and then we'll get us started the next class by doing some more practice with it as well. So for our first example, we're looking at faculty where there are 6 professors, 6 associate professors, 10 assistant professors, and 12 instructors. From that group, we're going to form a 4-person committee randomly. We want to find the probability that all of the committee members are of the same rank. So all of them are professors or all of them are associate professors. So they're all coming from that same designation. So first, just thinking through how I would write this in sort of like my X and Y idea. So my Y in words is going to be my number of ways to choose our 4-person committee. So before we even write out what X is, let's already think about what type of rule do I think I'm going to be using. Is it going to be a combination, a permutation, or the multiplication rule? So things we want to think through. How many total faculty do we have to choose from? Well, 6 plus 6 plus 10 plus 12. So I would have a total of 34 faculty members. We're going to choose 4 of them. And then a question we ask a lot is, can we reuse a choice? So once a person is selected to be on this committee, could I select the same person again? Well, that answer would be no, right? So we can't serve more than once. So we're not able to reuse things. So then this is giving me my N, and this is giving me my R. Now another thing we need to ask ourselves then, now that we have an N and an R, is does order matter? If I am the first person to be chosen for the committee, is that different than being the second person chosen for that committee? Or if I look at these 4 spots, does it matter which spot I fill, or is it the same? So if I look at these, each spot is really the same. If I'm on the committee, I'm on the committee. So then for that reason, order does not matter. So let's actually go through now and calculate what Y would be. Everything we've gone through here should be arguing for us to use a combination. So for our Y, we have 34 faculty members in total. Order does not matter, and we can't serve more than one time. We can't reuse spots. And we're choosing 4 people. So our 34 combination 4, just using our calculator, will get us 46,376 different ways we can choose a 4-person committee. Now let's actually focus on the problem at hand. We want to find the probability that all committee members are of the same rank. So X is just going to be the number of ways all 4 are from the same rank. So what this could mean here for us is they could all be professors, or they all could be associate professors, or they all could be assistant professors, or they could all be lecturers. Right, that's what it means. So it can be any of those 4, but it has to be all from the same one. So let's first figure out, well, what if I just wanted to find all professors? Well, there are 6 professors. I want them all to be professors. So I'm going to be choosing all 4 of them. For the same reason we talked about with y, we're going to be using a combination. So if I get that 6 combination 4, that's going to get me 15. But it could have been all associate professors. There's also 6 of them, and we would want them all to be associate professors. Combination for the same reason. So 15 ways of doing that. All assistant professors, well, for this one, this time there's 10 of those. And again, I want them all, so all 4 have to be. So if I do my 10 combination 4, we get 210. And then finally, if they're all lecturers, well, this time there's 12 lecturers that I'm going to choose 4 of, which gives me 495. But now the question is really, what do I do with these numbers? Let's focus on our word here, right? We're going to do this, or this, or this, or this. As soon as I'm seeing that word, or, that's going to be telling me that I want to add my values together. So we're going to be adding our values together here. So I'm going to add 15 plus 15 plus 210 plus 495 to give me a total then of 735 ways that they could all be of the same rank. Because then now for my probability, we're going to take our x that we just found over our total number of possible ways, or our y, of the 46,376 to give us a probability of a little bit more than 1.5%, 0.0158 for our answer there. So there's our first question that we're working through together here. Let's try another. So for problem 2, we have 4 heterosexual couples. So we have 4 husbands and 4 wives. And they're going to go to a concert together. And they have 8 tickets together in one row. So we have sort of these 8 seats all together. Right? All in the same row. So the first answer is no preferences or restrictions are given of who sits by whom. So I can sit anywhere I want. I don't have to sit next to my husband. I don't have to sit next to another woman. I'm not being picky at all about who I sit by. How many possible ways can we sit the 8 people? All right, so thinking through this, hopefully this will make sense where we can't sit in more than one seat. So in a sense, I can't reuse people. So once a person has taken up one seat, they're done. So I don't have to worry about that. So there's really 2 different ways to approach this problem. I'm going to focus on it first as an N and an R problem. Because since we just said we couldn't reuse things, that's making me feel like I have an N and an R. Well, N is my total number of people I have to choose from. So we have 8. How many are going to sit down, basically, or how many are going to be chosen? All 8 of them have a seat, right? So all of them are going to be chosen here. Now, if I'm trying to figure out how many different ways we can sit, right? If I sit here, that's going to be different than if I sit here, because I'll be sitting next to 2 people there, right? I'll be sitting next to 1 person here. So in a sense, where I'm sat is going to change who I'm sitting by. Even though I don't care who I'm sitting by, it still changes who I'm sitting by. So I am going to say then that order does matter for me. So how many different ways can we arrange these 8 people in these 8 seats? So that's just going to give me an 8 permute 8, which will turn out to be 40,320. Another way to approach this problem was just to think through the multiplication rule. So there's 8 different people who could sit in the first seat, 7 who could sit in the second seat, 6, 5, 4, 3, 2, 1. And then since everyone is sitting, so this person and this person and this person, that's why we're going to be multiplying all those numbers together. All right, a little bit more complicated. We want to figure out how many different ways they can sit if all of the women are going to sit to the right of all of the men. So we still have our 8 seats. But here's now what we know. They're kind of broken into 2 groups of 4. All of the women are going to be to the right of the men. So the women are going to sit over here, and the men are going to sit over here. So if I think about this very first seat, how many people could sit there? 4, right? It's no longer 8 because it has to be a man, and I only have 4 men. So once I've sat the first man, how many people can sit here? Again, it has to be one of the 3 remaining men. Our next seat would be one of the 2 remaining men, and then finally the last man would have to sit there. Moving over to the women, it's a similar idea. I have 4 women, so any of the 4 women could sit in that first seat. I have 3 women left, one of which will sit in that seat, 2 of which is left, and then 1 of which is left. And as we're sort of feeling here, we're going to be multiplying these different values together. But the big question is, what sign goes here? So between the men and the women, what are we going to do? Well, here's our question. Are we seating the 4 men and the 4 women? Or are we setting 4 men or 4 women? That's our big question. Right? All 8 people are going to sit down. So I'm setting the 4 men and the 4 women. So we're going to end up multiplying this one all the way through, giving us a total of 576 ways that we could seat the 8 people if all of the women are going to sit to the right of all of the men. Something that's good to try here for part C is to actually pause the video and try it on your own, and then you can always see if you match what we end up doing. Alright, so for part C, this time we want all the couples to sit together. So basically each husband and wife have to sit next to each other, and we're going to try to figure out how many different ways we can sit these 8 people. Although there are multiple ways to approach this problem, I'm going to be explaining it in the way that seems to make the most sense to the most students. So let's think through how we're going to start this. Husbands and wives have to sit together. Well, for this very first seat, anyone could sit there, right? Any of those 8 people could sit in that first seat. After we know, though, who sits there, that is going to affect here. So, for example, let's suppose in this first seat, the husband named John gets chosen to sit there. Again, keep in mind it could be any of the 8 people, but just pretend for a moment that it's John that gets chosen. Then how many people can sit in this seat? Well, right, we're forcing couples to sit together. So we can really think about this as being broken into 4 groups of 2 because we have 4 couples, and the couples have to sit by each other. So as soon as John has sat down there, there is only one person that can take this seat. Who would that have to be? That would have to be John's wife. Right, so once he sat down, she doesn't get a choice. She has to sit next to her husband. because we're forcing all the couples to sit together. So then now one person and their spouse has been sat. We have 6 total people left that could sit in this seat. Similarly, as soon as we know who sat down there, their spouse has to sit next to them. We have 4 people left. Any of those 4 could sit here. Once we know who has sat there, their spouse has to sit next to them. Finally, you have 2 people left, and their spouse has to sit next to them. And then finally, we're just going to be multiplying all the way through here, including on those blue lines, because we're going to sit this couple, and this couple, and this couple, and this couple. So we do end up multiplying all the way through here to find that our total number of ways to do this is 384 ways that the couples could sit together. All right, our last problem in this video. So for this one, we're looking at a multiple choice test. I'm sure we've all taken a multiple choice test before. This one has 5 questions on it, and for each question there are 4 possible answers. Think like A, B, C, D. Only one of those answers will be correct. And we're going to assume at this point that the student is totally unsure and is just really kind of guessing at the answers. So we're going to use those ideas to help us answer the questions that follow. So the first thing we're going to do is just figure out how many different ways can a student check off one answer to each question. Well, again, just first thinking through this, we have 5 questions. Question 1, question 2, question 3, question 4. So if you were just sitting down guessing, you're on the first question. How many different answers could you choose? Any of the 4 that were given. Okay, now once you've answered the first question, how many answers are there for the second question? Well, there still should be 4, because right, if I answer A in the first question, the answer to question 2 can still be A. It's not forcing like that elimination of choices as we go. We can reuse the same answer as we go through. So question 3 would also have 4 possible answers. Question 4 would also have 4 possible answers. And question 5 would have 4 possible answers. So then we can just multiply these through, since we're answering question 1 and question 2 and question 3. That and telling me to multiply there to give us a total of 1,024 ways that a student can answer those 5 questions. So then something a student might be interested in. I want to find the problem that a student gets all of the answers wrong. You were a horrible guesser and you got them all wrong. Well, y is going to be our number of ways to answer the 5 questions. Which we already have the answer to. That's what we just found above. That's going to be our 1,024. X is going to be our number of ways that all answers are wrong. So let's think through this one. Well, how many answers are wrong for the first question? Well, it says that of those 4 possible answers, 1 is correct. So that would mean the other 3 answers are wrong. So I could choose any of these 3 options. I'm going to get that first question wrong. For my second question, again, there's 4 answers. 1 is correct. So the other 3 are wrong. For question 3, also 3 wrong answers. 3 wrong answers for question 4. And 3 wrong answers for question 5. And again, since we're answering all the questions, we're going to multiply, giving us 243 ways that we could check off all wrong answers. So now it asked us to find a probability, right? A probability has to be between 0 and 1. So that's just going to be my 243 out of the 1,024, which if you were to convert this to a decimal, it's going to give us 0.2373. So about a 24% chance that you would get all of the answers wrong if you're just guessing. All right, last question. What is the probability that a student gets 2 answers correct and the rest incorrect? Okay, so let's think through this one again. Y is going to be the same that we already had before. We're still answering those 5 questions with 4 possible answers each. So that's not going to change my Y. X is going to represent the number of ways we get 2 correct, which would mean that we get 3 wrong. Right, so that's kind of like by default. The rest are incorrect, so the other 3 are going to be wrong. Let's start by approaching it the same way that we did above. Right, so here's my 5 questions. We're going to have 2 of them be correct and 3 of them be wrong. Well, above, all of the questions were wrong, right? So up here, this was a wrong answer, this one was wrong, this one was wrong, this one was wrong, this one was wrong. They were all wrong. Right, so actually I'm going to start with something that is something I actually have to think through first, which actually makes this question a little bit more challenging. Well, I know 2 are correct and 3 are wrong. So what I know is going to be going on here is that there's going to be 2 correct answers and 3 wrong answers. But which 2 questions are going to be the correct ones? It doesn't say that I got the first 2 correct and the last 3 wrong, right? It just says that I got 2 correct. It doesn't say where I got those 2 correct. So actually the first thing I need to figure out is how can I get 2 questions right? So the first thing I'm actually going to do is choose which 2 questions are correct. So which 2 are going to have a C attached to it. Well, we could kind of think through, we could actually count through this if we wanted to. So the first and second could be correct. The first and third could be correct. The first and fourth could be correct. I could go through and count this. But let's see if we can figure out how to calculate this without counting it. First question. If I were to get the first question right, can I get the first question right again? No, so I can't reuse choices, right? So once I've chosen one of these to be correct, I have to choose another one to be my other one that's correct. So I should be thinking this N and R idea. Right, so N is representing how many different questions we're working with in total. R is going to represent how many questions we're going to get correct, is 2. So now I need to figure out if order matters. Now what do I mean by that? If I were to get the first and second question correct, is that the same thing as getting the second and first question correct? Well, yeah, right. If these are both correct, it doesn't matter if I say I got the second one right and the first one right, or if I got the first one right and the second one right, that's the same thing. So since that's the same thing, there is really no order to worry about with it. So that's going to give me a 5 combination 2, which will give me a 10. Now again, what this 10 is telling me is that's just telling me that's how many ways I can put 2 C's and 3 W's on here. But that's not my final answer. So now what I know, for example, is now I know which 2 questions I got right. So I could just pretend now, well, I got the first 2 right and the other 3 wrong. But again, right, these 2 C's could be in any of the 5 spots. And this 10 is telling me, well, where I could have put those C's. But now to actually go beyond, could keep going, I can focus on a particular instance. So how many now correct answers are there for those correct questions? Well, there's 1 for the first correct answer, 1 for our second correct answer. Now the other 3, we're getting them all wrong. So there are 3 wrong answers to choose from, 3 wrong answers to choose from, and 3 wrong answers to choose from. And again, we're answering all the questions, so we are going to multiply. So this will give us 27. But so now I've got to figure out what to do. I have this 10 that I found before and this 27. So what we're actually going to do is we're going to end up multiplying those 2 values together. So to get our x is going to be 10 times that 27 to give us 270. Now I want to pause here and explain again why this itself down here is not the answer for our x. As soon as I put this 1 times 1 times 3 times 3 times 3, here is the information that I've just communicated to you. I got the first question right, the second question right, the third question wrong, the fourth question wrong, and the fifth question wrong. But it didn't say I had to get the first 2 questions right. So what this 10 is doing for me is basically figuring out then how many different ways can I arrange these 2 1s and these 3 3s that I have without me actually having to list them out. I could have gone through and listed it out. So, well, I could have got the first question right, so 1 option there. Second question wrong, so 3 options there. Third question right, so 1 question there. 3 and 3, but every time I do that, I'm going to have 2 1s and 3 3s. And so anytime I multiply those 5 numbers together, I'm always going to get 27. So I really don't need to keep doing that same math over and over again when I can just find out, well, how many different ways can I arrange those 2 1s and those 3 3s that are different, and then just multiply all my numbers together at the end. My guess is if we have a question, we'll want to start with this one together as a class to make sure that that's making sense and there's not more questions on that. Because now I have my answer. My probability is going to be our 270 that we just went through over that 1,024 that we had to begin with, giving us a probability of 0.2637. Alright, so that is where the video is going to leave off. Where we're going to start in class next time is practicing some more of these questions. We will first do a couple more together as a class, and then you'll get a chance to work in your groups on a few problems as well, while I'm around to ask questions of. But again, we'll start with that very last question on the multiple choice test to see if we have questions or need more explanation on where things came from.